Yet another flavor of exact recovery, although a lot of the details will be different. We'll have a fairly different flavor technically. So this is going to be back in the spirit of lectures 6, 7, and 8, where we took NP hard problems, posited extra structure on them, and then showed we could have polynomial time algorithms to get back the optimal solution. Those lectures focused on these different stability properties. So we had approximation stability for k-median, perturbation stability for both k-median and cut problems. So here we're going to be going back to graph problems, like we were studying in lecture 8. And we're going to be studying conditions that have the flavor of these stability conditions, I think in spirit, but technically they're going to be fairly different. They're going to be randomized models. So we're actually going to be looking at, we're going to posit a generative a distribution over graphs. And we're going to argue, we want to know, like with high probability, can we have polynomial time algorithms that solve NP hard problems like finding the maximum clique, finding the minimum bisection, that sort of thing. Okay. All right, so again, what we're trying to accomplish with this, these models is we want to have a different way of reasoning about graph algorithms, especially, so recall we talked about maximum weight independence set. If you don't make any conditions, if you just talk about approximation ratios, all algorithms have a terrible approximation ratio. There's no way to distinguish between them. So now we're asking, can we have a different model of inputs which allow us to get more informative analyses of algorithms and maybe suggest using one over another. And so we're going to think about distributions over graphs. Okay, so average case analysis in a sense. And if you want to talk about distributions over graphs, you have to start with an ErdosRenyi model. Okay? So we're not going to actually wind up using these, but it's important to understand what they are and why they're not sufficient for our goals of differentiating between different algorithms. So when people talk about the model GNP, okay, so there's two parameters, n and p. N is the number of vertices. P is the edge probability, or expected edge density. Okay? So there's n vertices, that's deterministic. And of the n choose 2 possible edges, for each of those edges you flip an independent coin. With probability p it comes up heads and you stick in the edge. With probability 1 minus p it comes up tails and you don't stick in the edge. Okay? And so you can go ahead and think about p equal 1/2 as a canonical case if you like. So each edge present, IID, probability p. Okay? So if p equals 1/2, this is in fact the uniform distribution over all of the undirected graphs in the world, turns out. Okay? All right. So this is the first place to start. There's a beautiful theory of ErdosRenyi random graphs. So how about using it for algorithms? And the problem, and for some computational problems, you can say some interesting things about ErdosRenyi graphs. But I'm going to pick a couple of problems where it's really not a very helpful model. Because it can't differentiate between different algorithms. Okay? And so this is true for, I'm going to show you 2 examples, but it's true for many problems, many NP hard problems. Let me show you a really extreme example. So let's talk about the min bisection problem. This means you want to find the minimum graph cut, except I'm also going to insist that the 2 sides of your cut have equal cardinality. Okay? Each one has exactly half of the nodes. Okay? So input, let's just focus on the unweighted case. Even number of vertices. And so the output should be a bisection S complement of equal sizes, minimizing the number of cut edges. Okay? All right, so why is this sort of not an interesting model to study algorithmically? So here's something, I'll sort of state it now and leave the details to the homework. It's a sort of straightforward exercise in probability, which is if you take a random graph from GNP, then with high probability, all of the bisections are pretty much exactly the same. Okay? So with high probability, every bisection cuts roughly n squared over 4 p edges. Get the door. So why is this true? So this is basically the, this is roughly the total number of edges, n squared over 4. Each one is, fix a bisection, n over 2 vertices on the left, n over 2 vertices on the right. This is the number of potentially crossing edges. Okay, you have a choice of one of n over 2 vertices on the left, one of n over 2 on the right. Each of those edges is present with probability p. So for a fixed bisection, if you then flip the coins for the edges, this is the expected number of edges that get cut by that particular bisection. So in expectation, every bisection is the same. And these random variables are well concentrated. Okay, so let's say if p is a constant. And so this will be the exercise on the homework, which you can prove using so-called Chernoff bounds, that there's very little difference between, all of these differ very little from their expectation. So suppose you had, different heuristics for minimum bisection, okay? And you wanted to say which one was better. Well, even if you had an algorithm where your bright idea was to compute the maximum bisection, that would be as good as any of these other heuristics, right? Because any bisection is as good as any other bisection. All right, so really there's just no way to talk about different algorithms in this model. Make sense? Okay. So they're just sort of not very interesting from the perspective of this problem. Here's another example, so a more interesting example. So this is a famous problem, actually. Whoops, not planted. Getting ahead of myself. Clique, max clique. Right? So you should all know this problem. It's just the complement of independent sets. So I give you an undirected graph. A clique is just a bunch of nodes so that they're all connected to each other, and you want to just find the biggest clique in the graph. Okay? So that's just as hard as independent set. What about in ErdosRenyi graphs? Okay? So it is easier. It's an easier problem in ErdosRenyi graphs, but somehow, again, it just doesn't force us to design interesting algorithms. Okay? We just don't learn anything illuminating by studying the problem in such graphs. So let me explain. So fact number 1. So let's just take p equal 1/2. Okay, so each edge is equally there or not. And g n 1/2. So what do we think the answer is going to be? So for bisection, right, we thought the answer was going to be n squared over 4 times p. Here it's a little less obvious. But I'll show you a heuristic calculation that we expect the max clique size to be roughly 2 log base 2 of n. Okay? So heuristic proof. So let's do something different. Let's actually just, for a given size of cliques k, let's just count how many cliques of size k are going to be in this graph in expectation. And let's just look at sort of like, what's the magic number of k for which we expect to be roughly one k clique. And we're going to heuristically interpret that as, sort of the likely size of the biggest k clique. It doesn't prove that, okay? It proves the correct answer, but it's not a proof of that fact, okay? But this gives you an idea of like, where does this number come from? All right, so for parameter k, how many k cliques are we going to see in a random sample from G and P? Well, how many opportunities for a k clique do we have? For the n vertices, so there are n choose k ways of choosing a subset of k vertices. That's a clique if and only if every single one of the edges amongst those k vertices is there. There's k choose 2 edges that need to be there for it to be a clique. Each is there with 50% probability. So for a given choice of k vertices, it is a clique with probability 2 raised to the minus k choose 2. Okay? So this is exact. So this is the expected number of k cliques. let's just kind of do some sloppy estimations. Let's say this is like n to the k or so. Let's think of this as like k squared over 2. So now the question is, so we want to know when is this 1? For what value of k is this equal to 1? That's the same thing as saying for what value of this, so for what value is this going to be n to the k? Or sorry, for what value of k is this term equal to the reciprocal of this term? And that's going to be when k is like 2 log base 2 of n. Okay? You can plug this in and check. All right? So fine. In fact, I mean, just a little trivia fact. It turns out that, so again, we didn't prove it, but it is true that it's very likely that the maximum clique is going to be around this number. In fact, it's one of the most concentrated random variables you'll ever see. All right? So with probability tending to 1 as n grows large, it's either the floor or the ceiling of that number. Okay? So it's one of 2 numbers with overwhelming probability. And you start seeing stuff like that, you're like, maybe this uniform distribution over graphs isn't actually giving me good information about graphs that I encounter in real life. It's a beautiful model, but there's not a lot of real-world distributions over graphs for which it's a good first-order approximation. Okay. So that's fact 1. The target, so if we're running an algorithm for max clique on ErdosRenyi graphs, this is sort of what we're shooting for. We'd like to get as close to this as possible. All right? Now, it turns out so we don't have any algorithm that can get this, which is okay. I mean, it's not clear that we expect this problem to suddenly become easy, like polynomial time solvable in ErdosRenyi graphs. But what's frustrating is, no matter how smart or stupid your polynomial time algorithm, everything gets exactly the same performance, which is you get 1 times log base 2 of n. Okay? So fact 2, all heuristics get stuck at log base 2 of n, more or less. Including, for example, and I'll ask you to analyze this on the homework, just the obvious greedy algorithm, where you pick a node, you take an arbitrary node that's connected to it, you make that a 2 clique, you try to find a node that's connected to both of them. If you find one, that's your 3 clique, you try to find a node that's connected to all 3 of them, and so on. And you can just do that until you get stuck. That's going to get stuck at like log n, turns out, and we don't really know how to do better. Nor do we know how to prove. This would also be super interesting. So it would be super interesting to do better than that. It would also be super interesting to say, if you could do better than a 2 approximation, some other unlikely consequence would happen. But because this is sort of an average case problem, we don't really know how to connect average case problems to kind of NP completeness. So there's no connections between making progress on this problem and making progress on, say, SAT. Okay? So there's some really nice open problems there, but at the moment, the state of the art, trying to come up with clique algorithms on ErdosRenyi graphs has not led us to any interesting new results. Okay? Is that a product of our lack of imagination, or is it something more fundamental? It's a good question. Okay? All right. So that's what I want to say about ErdosRenyi graphs. Okay? So if you're talking about random graph models, and you're going to do something other than ErdosRenyi, you have to explain why. And so hopefully now I've explained why. Okay? It's not good enough. So how are we going to change the ErdosRenyi model to hopefully get more interesting algorithms? So the next thing we're going to do is talk about planted solutions. Okay? All right, so problem, can't differentiate between different algorithms. Fix. We're going to plant a clearly optimal solution. Okay? And we're going to ask a polynomial time algorithm to recover it. Okay, so again, this is, I think, very much in the spirit of the lectures on stability properties, stability assumptions. Okay? So let me show you the planted version of both minimum bisection and max clique. They're both quite nice problems. So example, planted bisection. And so this was studied all the way back in the early to mid 80s even. So what we do, so this is how we generate an instance. Okay, so if you like, there's again going to be a distribution over graphs, okay, but it's going to be non-uniform. So here's how you sample from this distribution or generate a graph from this distribution. So you first partition V into S1 and S2, where these have equal size. Okay, so you can do this randomly or you can do it arbitrarily. By symmetry, it's not going to matter. Okay, so there's some sort of target partition. Okay. Now, how do we make this? Okay, so that's our plant. How do we make sure that it's clearly optimal? Well, rather than picking every edge with the exact same probability, we're going to bias the edges so that we're much more likely to see edges inside S1 or S2 than we are to see edges crossing between S1 and S2. This is how we'll ensure that this bisection cuts fewer edges than anything else. Okay, we're going to bias the distribution so that the bisection is sparse. All right? So edges inside S1, S2 with probability P. Between S1, S2 with some probability Q less than P. All right? So we have S1, we have S2, possibly pretty dense inside, but fairly sparse between them. Okay. Now, needless to say, the algorithm isn't presented with the graph with a nice picture like this. Right? These things are all scrambled together. And so the question is, can you figure out where, like even I tell you there's one of these sparse bisections, but you know, there's a lot of bisections to try, so can you quickly find that sparse bisection? Okay? So the theory question that's sort of really nice to think about then is something very clean. Okay, so hopefully it's clear that this problem is going to get easier and easier as the gap between P and Q grows. Okay, so this bisection will be more obviously there the bigger the differential between the density of edges across the bisection and those inside the clusters. So obviously if P and Q are the same, right, we sort of argued it's not an interesting problem. And if they're super far apart, then presumably trivia algorithms work. So the question is, what is the gap between P and Q that's necessary and sufficient for exact recovery by a polynomial time algorithm? Elliot.
So what is the reason for creating these graphs that are very contrived and then trying to find the algorithms?
That's an excellent question. So I thought about sort of talking about this at the beginning. So, right, so if we think about where do these, so this is now I think the fifth lecture we've had basically on exact and approximate recovery. And I think you're right to point out that there's sort of a shift here. So we had these three on these stability notions where we sort of argued, it's like, well, if you think these are interesting problems to solve, you're implicitly making these assumptions anyways. And that's kind of where the story came from. Plus, I don't know, there's some kind of intuitive appeal to that at least maybe approximate versions of these stability notions might hold for, say, clustering problems that we care about. Then we had last lecture where, our sufficient condition was a little hard to get our head around, these almost Euclidean subspaces, but at least we sort of proved that the ends justified the means. Right, so basically it allowed us to solve the problem that we wanted, and it holds for lots of random matrices. And I think the models we're talking about in this lecture don't really satisfy either of those criteria. These, I think, are more, so sometimes when you're stuck on a problem, right, so when all of your current theories are failing, it can be a useful exercise to kind of invent a model which seems likely to force you to design new algorithms. Or again, even I'd say, maybe you even have a sense that one algorithm is better than another one, and you're just sort of looking for any rigorous justification of that fact to sort of separate the two of them. And in that sense, the models I'm going to be describing today, I think, have been successful. I think, for example, for the maximum clique problem, there's been some interesting algorithms that have come from, so we're in sort of part 2 out of 3 of this lecture. So this is the planted models, then we're going to have these semi-random models. So once we pass to the sort of most robust model, there have been interesting clique algorithms that have emerged from the study of this model. And it's also the case that these semi-random models identify a sense in which a certain more sort of sophisticated algorithm is better in the sense of being more robust than simpler, more brittle heuristics. So I think more than any of the lectures of this exact recovery sequence, we're sort of not really believing that real instances conform to this model. So more than, all of them require a bit of a leap of faith. But here I'd say we're not even trying to spin a narrative about what this has to do with it. We're really just saying, look, clique is kind of a disaster. It's inapproximable. You can study these special cases, but we're not getting anywhere. And so this is sort of a novel angle, I would say. But it would be nice. So you could imagine studying kind of stable, stability notions in the context of the clique problem. I'm not sure if that hasn't been done, or if it's just sort of winds up not being interesting, and that's why there aren't results on it. But I think there's definitely room to try to take the conclusions of today's lecture, which are some justifications of some algorithms and differentiations between different algorithms, and try to recreate those in a model of data which has more intrinsic appeal. I think that's definitely, would be a very nice, thing for someone to do. Yep. Any other questions? Okay. Right. So this is just kind of the challenge problem. It's like, all right, we don't have good guarantees from in bisection. Can you at least give me an algorithm that does me this once P and Q are sufficiently far apart? Okay. All right. So question, right. How big does P minus Q need to be? Need to be in order for there to be a polynomial time algorithm for exact recovery. Okay, so I'll tell you the answer to that question a little later in lecture. Let me talk about the planted version of clique. And so the planted clique version, the planted clique problem, has actually, it's turned out to be a very intriguing creature, actually. And I'll say a little bit about that. So here's how this works. So there's some parameter k, and what you do is you plant a k clique. So you pick a subset of the vertices. Okay, so you just have some, you think of it, you start as with ErdosRenyi, you start with n vertices and no edges. You pick a subset of size k. Again, you can pick randomly or you can pick arbitrarily, it doesn't matter, by symmetry. You make C a clique. Okay, so that's the planted clique, k clique. And then for every other edge, you include every other edge outside of the clique with probability P. Okay? And think of P as 1/2 for the clique problem. So here, the picture is, you have this clique, and then it's sort of buried in some fairly dense, if P is 1/2, fairly dense sort of ambient graph. Okay? And you're supposed to find it. And again, what's clear, hopefully, is that the bigger K is, the easier this problem is. Right? So like if K is too small, if K is like at most log n or something, it's just going to be totally hidden in this random graph if P is 1/2. Right? It already had plenty of cliques of that size, so you're not going to find this one. Good. And so now the question is, how big does K need to be before there exists an algorithm that does exact recovery with high probability? Okay? All right, so are those two problems clear? Okay, so what I'm going to do next is I'm going to give you an algorithm that solves planted clique for K sufficiently large. But the algorithm is going to be a kind of unsatisfying. And that's going to motivate our third genre of models, these semi-random models. Okay? But let me show you actually a positive result for planet clique. Actually, let me point out some structural properties that these instances of planet clique are likely to have, and then the algorithm will just sort of reveal itself. All right? So, suppose you took a sample of a graph like this. Okay? Take p equal a half. Okay? And suppose you looked at the vertex degrees, so the number of incident edges, and you sorted the degree sequence from minimum degree to maximum degree. Okay? What's the expected, so again, p is a half. What's the expected degree, basically, of a given node in this graph? Without the clique. Sorry, no clique at the moment. Okay, just g and 1/2. N over 2. Yeah, n minus 1 over 2. Right. Okay, so like n over 2. So this is going to be the average degree. Okay, so degrees. Good. What's going to be like the standard deviation of the degree, you think?
Square root of that.
Square root of n, yeah. Times a constant. Yeah, all right? So you're expecting a deviation of like root n, okay? So over here you have this minus root n plus root n. And if you plotted, you'd have a whole bunch of stuff around here, and you'd still have plenty of stuff within a standard deviation. Okay? Now, I'll leave this as an exercise, but if you want to know when does this die out, right, so where's the minimum degree going to be and where's the maximum degree going to be? This is going to die out after about square root of log n standard deviations by Chebyshev's inequality. Okay? So this is just an ErdosRenyi graph. Okay? So no big deal. So this doesn't, so what? Here's the point, okay? Now, so the way I described it here is I planted the clique first, and then I sort of flipped coins for the ambient edges. Do them in the reverse order. Okay, it doesn't change the distribution. Okay, so imagine you pick a sample from G and 1/2, and then you plant a K clique. Okay? Now, suppose you've done the first step, so you've picked your random graph, the ambient random graph. Now, suppose you were not one of the lucky fellows in the K clique. What happens to your degree? Nothing, right? Okay, you don't get any new edges, right? What if you are in the clique? What happens to your degree?
At least K.
It goes up. Like maybe you're already connected to some of those guys in the ambient thing, but it goes up significantly, certainly by like K over 2 in expectation. Because it goes up by like a lot. Okay? Constant times K, all right? So, in terms of this picture, that means anybody not in the clique stays where they are. Anyone who is in the clique jumps K spots or constant times K spots that way. So once K becomes a constant times the square root of n log n, even if you were the least popular node in this graph, you will catapult past everybody who's not in the clique. Okay? So the upshot is that when K is at least a suitable constant times square root of n log n, what's the algorithm?
Just take the nodes of the highest degree. The K vertex is the highest degree.
Yeah, exactly. Take the K nodes of the highest degree. With high probability, that's going to be the planted clique. Okay.
The square root of n log n is very large.
It is. It is. It's still, the good news is if n is big, it's a very small fraction of the graph.
It's much larger than I think our log n result that we got earlier.
It is, well, we didn't get a log n result, to be clear.
Sorry.
We just said that, you mean this, if you want to call that, we didn't recover anything. So I guess in ErdosRenyi graphs, there's this 2 log n clique and we don't recover it. Okay, so there's sort of like no recovery statement.
It's much larger than the clique you'd expect to exist.
Yes. Well, so right. So let's put it this way. You might hope you could do it for K much smaller.
Yeah.
like k, maybe even like 100 log n. Why not, right? It's intuitively it should dwarf what was there before, even if it was 100 log n. Okay, so so one thing that's unsatisfying, which I'm sorry to say I won't be able to satisfy you this lecture, is that this is big. Okay. A second thing which is unsatisfying is, you might want to have a smarter algorithm than this, right? I mean, you could probably find real-world networks where actually this would do reasonable things for finding dense subgraphs. But people who find dense subgraphs, on actual, say, social networks, they do things that are smarter than this. Okay, so you'd like to actually have the theory kind of force you to do something smarter than this as well. This feels kind of brittle. Okay, and actually these semi-random models will make precise a sense in which this is brittle. Okay. All right, so that's an exact recovery result in a planted model. It's not totally satisfying, but it's something.
In this model, are there better results?
There are. That's actually the next thing I was going to say, which is, I shouldn't say sophisticated, but sort of more non-trivial algorithms work for k constant times root n. Okay? So it is known how to shave the root log factor. Right? And again, you might hope, it seems like if k is 100 times log n, you should be able to do it, right? So it's not, I'm not expecting you to be blown away by the root n. Nobody knows whether or not it's possible to recover planted cliques with high probability and polynomial time for k less than root n. I think people generally think perhaps it's not possible, but again, because it's an average case problem, we don't really have complexity theory that would allow us to prove that. Okay? So we neither have the language to prove it's impossible, nor do we seem to have any good algorithmic ideas about how to do it. Okay, so it's a sort of interesting problem that really just seems beyond the reach of state-of-the-art techniques, upper or lower bounds. Okay? In fact, it's gotten to the point, people are frustrated when they stop trying to resolve a result in either way and just start using it as an assumption to prove other results. Okay? And that's sort of the state of the planted clique problem circa the last less than a decade. Okay? So the first result of this sort was, you started having people, there's definitely like a crypto system, not a practical one, but a theoretical one, where you can show that the security of the crypto system can be laid on the hardness of finding planted cliques for k well less than root n, so that can be done. There's been some really interesting connections people have developed just over the past few years. So, for example, there's a connection between finding planted cliques and computing Nash equilibria of certain sorts in various games. And also recently people have actually connected the hardness of finding planted cliques to the hardness of certain statistical estimation problems. Another very interesting connection. Okay? So to answer the question about, when you ask someone to defend a model and sort of like the biggest cop-out answer you can ever give is, oh well, it might lead to interesting connections someday, right? So that's kind of like, if you have nothing else to say, and that's like your last resort defense. But then, sometimes it's true. So, Karp proposed the planted clique problem back in '76, and just really 21st century, it's just taken on this new life and being much more richly connected to issues in different communities than I think anyone realized, even say 10 or 5 years ago. So sometimes if it just feels like a natural model, it can be worth investigating. Again, you should always strive for a stronger story than that, but sometimes things are connected even when you don't know it. Okay, so open, close gap between O of log n versus omega root n. Okay, so that's a major open question that really no one has any clue, I don't think, about how to improve either the upper or the lower bound. Okay. So now I want to talk about semi-random models a little bit. Any questions? All right. So semi-random models. This is in the spirit of one of the recurring themes of the course, which is finding clever hybrids between average case and worst case analysis. So we can sort of think of these planet problems as basically average case analysis. The distribution we're doing an average case over is, kind of a, it's an unusual distribution. It's not uniform. It's with this planted clique or planted bisection. This has a partial worst case flavor to it, which again, the goal is to sort of drive us toward even more robust, even more interesting algorithms. And it's been reasonably successful in that regard. Okay, so there was an early paper by Blum and Spencer, and I'm going to be talking mostly about stuff from a paper of Feiga and Killian. So let me explain how this works simultaneously in both the bisection and the clique problems. So first, there's both nature and there's an adversary, okay? Where the adversary is trying to devise a bad input for your algorithm, okay? So nature goes first. So you start with a random planted instance. Could be clique, could be bisection, whatever. Then nature hands over its sample to the adversary. Okay? The adversary gets to change the input that nature started with. Now, of course, the adversary shouldn't be allowed to change it in a totally arbitrary way, because then it could just throw nature's sample in the garbage can and give you a worst case instance. Okay? So it has to sort of partially respect the randomness in nature's sample. So what the adversary can do, this is going to sound funny when you first hear it. The adversary can take the dense regions and make them denser, or the sparse regions and make them sparser. So like in the bisection picture, where we have this planted bisection, dense regions in the inside, sparse across the bisection, the adversary can add more edges inside S1 or inside S2 if it wants, or it can remove edges from crossing the bisection if it wants. For the clique, it can't screw up the clique, it has to leave the clique there. Any other edges, it can delete it if it so chooses. Okay?
So in this sense, the adversary knows the certificate or the planting.
Yeah. Yeah. And has to respect it. So again, certainly not like any kind of literal model for how data is constructed. Yeah. Okay. So why? Well, I guess a couple things. So first, this is just a quick observation. So can the adversary change the optimal solution? No, it just makes the optimal solutions even more pronounced. Okay, so that's what it sounds weird at first. Like it sounds like, why call it an adversary if it can only help you out, right? On the other hand, maybe there's some algorithms which work in the planted model and don't work with this adversary in a semirandom model. In fact, if you think about it, and this is an easy one, but I'll ask it on the homework anyways. Top k degrees no longer works for clique. Okay? So if there's an adversary and your algorithm is a top k degrees, you might actually return something other than the planted clique. Forget about root n. Even if the clique has linear size, you might not get it with this algorithm. Okay? So again, this model has allowed us then to take an algorithm which intuitively felt like it was kind of cheating. It was kind of really using detailed statistics of the distribution over inputs, and therefore was sort of a brittle solution. And so this was a way of saying, no, that's not a robust enough algorithm. For example, if you had some adversary tweaking with the input in an intuitively helpful way, all of a sudden the algorithm stops working. We'd really like algorithms that are robust. What does robust mean? Well, it can mean a lot of things. This is one notion of robustness. Okay? It sort of says your algorithm's success should have monotonicity with respect to the easiness of the input. That's basically what we're saying. Okay? So that's what we want. Okay. So interpretation, only robust algorithms will survive. I mean, I guess in general, I mean, this has been, these planet models, this is one of the first examples we've really seen where we posited distribution over inputs. We haven't done that. We had a number of lectures where we just allowed any inputs. In parameterized analysis, we never restricted the inputs. We just analyzed the performance of an algorithm in terms of some easiness parameter. More recently, we've been having some actual restrictions on inputs, right? Like say, even earlier this lecture, right? We claim nothing for arbitrary, sorry, earlier today. We claim nothing for arbitrary constraint matrices. In effect, we were saying like, let's only solve the problem in this restricted family of inputs. But there was, there was sort of a distribution last lecture over A's, but think of the stability properties, right? There was no distribution. It was really just a subset of instances we were solving exactly. Here we're doing flat out average case analysis, right? There's a distribution over inputs. We know what the distribution is. And we sort of tailored our algorithm to exactly what that distribution over inputs is. And we're going to develop this theme more strongly as the course goes on from now. But basically, the theory that I'm sort of curating for you in this class is meant to prevent you from designing algorithms which are too overly fitted to any particular distributional assumption. And so you want to sometimes build into your analysis framework or your model of inputs kind of safeguards that prevent you from designing algorithms which make overly detailed use of the distributions. These semi-random adversaries are one, fairly successful and fairly generally applicable such safeguard. Okay. All right. Questions? All right, so for the rest of the lecture, I want to talk about some positive results for min bisection. I guess I'm not gonna plan on saying more about clique, but let me just mention for clique, it is known how to again get this k equal to root n with a semi-random adversary. Okay, those are some nice results. Okay, they're a little lengthy to present in a lecture here, but they do exist. Okay, so the root n can be achieved in the semi-random model, and no one knows how to do better even in just the regular planted model. Okay. So I want to talk about min bisection the rest of the lecture. So is everyone clear on the model we're studying? Okay, so this is, we have the P and the Q. It's this dense parameter P inside the planted bisection. It's the sparse Q across the bisection. An adversary can delete stuff from the bisection or add stuff inside a cluster. Okay? And so we want an algorithm which recovers the planted bisection with high probability over nature's moves and for arbitrary then additions and deletions by the adversary. Okay. So min bisection. So here's the regime we're going to work in. Assume that P and Q are constants. So remember that means that the edge is going to be fairly dense, right? So there's going to be some constant density inside each component and some lower density, but constant density across the bisection, such that. So again, remember, it's going to get easier the bigger the gap between P and Q. So we're going to insist that the gap between P and Q is at least some constant times root log n over n. Okay? So this is some constant. You don't actually, this is just sort of for full disclosure. You're not actually going to need to know this in the proof that I'm going to do. The one thing I want to point out is, this is a small gap. Right? So P and Q are constants. So this is certainly much stronger than saying, assume there exists some constant 0.01 such that P and Q are at least 0.01 apart. Right? This is going to 0 with n. Okay, the gap. Okay? So that's satisfying. We don't need the gap to be big to get a recovery result. And it's also satisfying in that, if we went below this, okay, then we'd have this very awkward situation where, we have this intended planted bisection, but then once we flip all the coins, actually something else winds up being the minimum bisection. Right? So think about it as if P equals Q. and we're back in ErdosRenyi, and you try to like, plant a target bisection, like nodes 1 through n over 2, and then nodes n over 2 plus 1 through n. Like, oh, that's my secret planted bisection. But then you flip all the coins, everything's symmetric. So every bisection is equally likely to be the minimum. It's not going to be the target one you picked in the front at the beginning. And similarly, if P and Q are too close to each other, you're going to have that same problem. Some other bisection other than one you intended is going to wind up being minimum. So like, if you want to have a recovery result of your planted bisection, it better at least be the minimum bisection. Okay? And this is, ballpark kind of the gap you need for even that weaker property to be true. Okay? So this at least lets you have the bisection is the one you intended, and that's also where you start getting polynomial time recovery results. Okay? So necessary for planted to be the minimum. Okay? So that's also satisfying. Okay? All right. So this problem will give me the opportunity to talk a little bit about what's called semidefinite programming, which is a really key tool for a lot of the state-of-the-art exact recovery techniques. Okay? I may talk more about this next week or not. I haven't decided. So for short, everyone calls this SDP, semidefinite programming. Okay? Let me explain. Okay, so just a couple of words of context. So semidefinite programming is, you can think of as a generalization of linear programming. So it allows you to solve even more stuff, but it's still polynomial time. It's not quite as efficient in either theory or in practice, but it's decently efficient in both theory and practice. Okay, so it's definitely, you can solve decent-sized problems with semidefinite programming, okay, in practice. So it's heavy machinery, but really is used to solve problems if they're not too huge. And rather than tell you what they are, let me just let's talk about bisection. And let me just tell you about sort of a formulation of bisection, and then we'll explain how that leads to a certain relaxation, okay? So motivation. So fix a graph, even number of nodes. Let's look at a particular bisection, okay? SS bar. So let me encode it algebraically as follows, okay? So Z is going to be a plus minus 1 vector indexed by the vertices. And this is just the characteristic vector, saying which node is on the left side and which node is on the right side. Maybe plus 1 means you're in S, minus 1 means you're in S bar. Okay, so a bisection induces a plus minus 1 vector like this. Now define, and it's not going to be immediately clear why I'm doing this, but I want to look at products of pairs of these zi's. Okay, so for a pair of vertices I and j, define xij to just be zi times zj. Okay, so also a plus minus, either plus or minus 1. Okay, and it's going to be useful to think of the matrix of all of the xij's. So if X denotes the matrix of all the xij's, so this is indexed by vertices, both on the rows and on the columns. This is just the outer product of the z vector. Okay? So ZZ transpose just means the matrix of the zij's. Okay? All right. So, okay, you can do that. Now what I'm going to do is I'm going to write down a few constraints that these x's satisfy, starting from any bisection. Just like when we were talking about linear programming relaxations, we always had in mind intended semantics. We're like, okay, if you have a multi-way cut, then these things are zeros, these are ones, blah, blah, blah. And then ultimately you optimize over some bigger set that includes those canonical encodings of discrete solutions. Okay, so we're doing that same program now. It's a little more complicated, but it's exactly the same idea. So this is our encoding of a bisection. Let me now show you constraints satisfied by any bisection. Okay. Actually, first let's just notice that we can express the objective function Okay, we remember it's bisection. We want to minimize the number of cut edges. We can express that very cleanly in terms of the x's. By the way, if it helps to open the door, that's fine too. So if it's getting stuffy in here, I don't know. But I'm assuming the conversation has died down out there. So, okay. So how can we express, thanks. So how can we express the objective function, the number of edges cut, in terms of these x's, okay? Well, if an edge is cut if and only if its endpoints are on different sides, if and only if its zi and zj have opposite signs, so if and only if xij equals -1. Okay, so the cut edges have a -1 and the non-cut edges have a 1. So the sneaky way of writing that would just be 1 minus xij, so this is either 0 or 2, depending on whether it's cut or not. So I'm going to divide it back by 2. Okay? And I'm going to sum this over the edges, I, j, and e. So call that 1. Okay? So that's nice. Have a nice linear objective in the x's, expressing exactly what we care about. So now let me list the constraints. And there are 3 constraints. Let me mention the simple ones first. So first of all, xii equals 1 for all I. That's just because xi is zi times zi. And zi is plus or minus 1. 3 is if I sum up all of the entries of this matrix, then I get 0. And that's because I started with a bisection. Okay, so one important thing is that the z here had an equal number of plus and minus 1s. Okay, which means that also in the x matrix, I'm going to have an equal number of plus and minus 1s. Okay? So sum over all xij equals 0. This is not that important. This is important. It's saying that x should be balanced and z should be balanced. Okay? Which that's encoding the bisection idea. Now over here, I sort of want to have some constraint which expresses the fact that this x matrix is not arbitrary, but rather it arises as the outer product of a vector. Okay? So notice, right, in general for a matrix with n squared entries, I have n squared degrees of freedom, but for matrices that arise as outer products, there's only n degrees of freedom, right? What do I populate the different entries z's with? So I want to somehow say this matrix is structured, comes from this subset. Now I'm not going to actually write something down which says x is of the form x equals zz transpose. Okay? That would be a nasty constraint, which you cannot optimize over in polynomial time. So I'm going to write down something which is more relaxed, which is that the matrix X of the xij's is symmetric and positive semidefinite. Okay? So if you've forgotten what positive semidefinite is, probably the best thing to do is just after class go look it up on Wikipedia. But basically, so that means a bunch of things, right? So one definition you might have seen is only non-negative eigenvalues, or maybe like a non-negative quadratic form. I mean, the way to think about it here, positive semidefinite means, okay, you might be an outer product. That's a special case. In general, you're like the superposition, i.e. the sum of a bunch of outer products. Okay? That's the extent to which positive semidefinite is more general than what I've written there. It might not just be one outer product, maybe a bunch added up. Okay? And that's if and only if. All right? Okay. All right, so now we're going to note by SDP the optimization problem of minimizing the objective function 1, which is linear in the x's, subject to the constraints 2 through 4. This is linear in the x's, this is linear in the x's. This is something you may not have seen before, but it turns out This is a nice set. Okay, the set of symmetric positive semi-definite matrices is convex, which is sort of the most important point. It's actually a cone. And because you have, okay, it's not linear, but you have this convexity, that actually means you can still solve this problem in polynomial time, up to additive epsilon error. Okay? So fact can be solved in polytime. And again, this is even more general than linear programming. As I said last week, we're going to think about linear programming as most people do, as a black box. Certainly, we're going to think about semi-definite programming that way. Okay? All right. So any questions about that? So I hope it's clear that, there's no contradiction that we can solve this in polynomial time, and the fact that min bisection is NP hard. Right? If we solve this optimization problem, we will not in general get back something that corresponds to a bisection. If we're really lucky and we solve this problem and we get back a matrix X, which happens to be rank 1, meaning which happens to be expressible as the outer product of some vertex z transpose, vector, z transpose, then it's going to be a bisection. That's the lucky case where we solve the problem optimally. If instead we solve this optimally, we get back a matrix X which has rank bigger than 1, meaning it's the sum of more than one outer product, then there's no way to interpret that as a bisection. It's kind of some distribution over bisections or something like that. Okay? Yeah?
But we are able to solve it integrally for z.
No.
Okay.
I shouldn't have said distribution over bisections, actually. That was incorrect. So in general, we're going to get back fractions. Okay, so in general, we'll get, so the z's actually are not decision variables of the semi-definite program. Mm-hmm. Okay? I did that just to kind of motivate, I did that to point out that any bisection can be thought of as one point in the feasible region here through this correspondence. Okay? So the program itself consists only of these n squared variables, the xij's. So you solve it and you get back some arbitrary, not arbitrary, but you get back real numbers in those xij's that are promised to satisfy 2 through 4. So I'll leave it for you to check that if in fact x is rank 1, then in light of these other constraints, is this true? I don't think it was true. I think it's true that if you get back a rank 1 solution, then the only way that can happen is if it's actually minus 1s and 1s. But I'll have to think about that. So anyway, so the thing which I need for the lecture is just that any feasible solution to the bisection problem maps onto a feasible solution of this problem. Okay? And therefore, if we minimize this, it's a relaxation. In that sense, this is a relaxation. Okay? So if we optimize over this, the optimal objective function value is going to be only less than the number of edges crossing the bin bisection. That's the key point. Okay? Good. Any other questions? Yeah.
I feel like the use of semi-definite optimization has not been motivated here, because it's not clear to me why something simpler wouldn't work like a linear program.
Yes. So right. I believe there are counterexamples for linear programming. It's an excellent question. So you're right that the first thing you'd want to try is a linear programming relaxation for bisection. And there are relaxations that have been used to design heuristics. I am unaware, they have not been used to successfully design exact recovery. And I think that's because they just don't work for exact recovery. But actually, I haven't worked out those counterexamples.
Even for larger gaps between P and Q?
That's a good question. Is there some bigger gap for which a linear program would work? It's a good question. I don't know the answer.
Okay.
Yeah. Okay. So let h of g be the opt value to SDP for a given graph g. Okay, so for any g, we can form this semi-definite program. Let this be the minimum objective function value of any feasible solution. And then b of g be the value of the min bisection. Okay, so the actual number of edges at minimum crossing any bisection. And what we have, by virtue of this being a relaxation, h of g is at most, right? So we're minimizing over a bigger set, it can only be smaller. Okay. Good. Okay, and so what we're shooting for is we want to show that as long as P and Q are separated by at least that gap, in fact, this is going to be exact. Okay? In fact, h of g will equal b of g, even though we really have no right to expect that. Okay? All right, so here's the key lemma due to Faga and Killian, which says that let's just consider the usual planted model. So forget about the adversary for the moment. Okay, so just the planted bisection model where P and Q are separated by at least c times square root of log n over n. Okay? So for the planted model, no adversary, with P and Q with that gap, this relaxation is exact with high probability. Okay? So this turns out to be true. Okay? This is not easy to prove, okay? And we're not going to prove it. This would actually be a great thing to prove in an advanced class, all right? So let me just say what the high-level idea is. So some of you know at least that linear programs have duals. Semidefinite programs also have duals, okay? And if you, in general, if you sort of want to say, so what do we want to say here? Basically, like, in the planted model, we have this, we know the answer to the integer primal problem, right? We've planted the bisection, right? So we know what we want to be optimal. And so we have this relaxation, but we want to say, yeah, but this integer thing is the optimal solution to it. All right? And if you think about it, duals are exactly what lets you certify that some proposed feasible primal solution is optimal. Okay? You exhibit a dual, you check that it's feasible, either you verify complementary slackness conditions, or you compute its objective function and show that the objective function value is the same as the primal. If you do either of those two things, that's a dual certificate of the optimality of your primal solution. So what this lemma needs to do is it needs to say this integral bisection feasible solution is actually optimal. So the way it proves is that you just sort of guess and check a suitable dual. Okay? So you have to figure out what the dual of this semidefinite program is. That's not that hard. It's actually pretty easy to guess what the right dual should be, the dual certificate, and compute the objective function value, but it's really annoying to check that it's feasible. In particular, to check that you get the sort of necessary positive semidefinite constraint. Okay, that takes a lengthy calculation, which I'm not gonna subject you to. Okay? The reason I say this would be a good thing to do in a more advanced class is actually a lot of the state-of-the-art exact recovery results follow exactly the same template. Okay, you're looking at some mathematical programming relaxation, like a convex relaxation, and you know what you want to be optimal, and the way you actually prove it is you literally, exhibit the dual. Okay? And there's a lot of kind of nice machinery that's been built over the last few years about where do these duals come from, how do you actually check the feasibility and so on. Okay? So guess and check suitable dual. Technical. Okay, so we're just going to accept that this is true. Faga and Killian prove this. I mean, it's in the paper if you're interested. Okay, but it takes some lengthy calculations. So what I want to do, but remember, this is for the planted model. Okay, this is not for the semi-random model. So the thing I do want to show you in lecture is I want to show you how, given that the semidefinite program is exact for the planted model, then it turns out it's also going to be easy to extend that to exact recovery in the semi-random model. So remember, the semi-random model was guiding us to sort of robust algorithms whose correctness was sort of monotone in the input in some sense. And I'm going to show you that the semi-definite program's exactness property has exactly this monotonicity type behavior. Okay, so that's what I want to leave you with. Okay, so here's a simple thing, which I'll leave for the homework, which is, so what can the adversary do? The adversary can add edges to the dense regions or delete edges from the sparse regions. Okay, so we want to think about the adversary adding or deleting edges, we know how the min bisection changes. It doesn't change at all. Right? So the adversary is restricted in a way that the true minimum bisection will never change. So instead what we want to do is we want to see how the semi-definite programming relaxation changes when the adversary adds an edge to a graph or deletes an edge to the graph. So the key but easy property is that if G hat is formed by adding one edge to a different graph G, well, then the semi-definite programming relaxation doesn't change in a very radical way. Okay? So we've added only more edges to the graph. You'd sort of think then that the optimal objective function value would only go up. There's only more things to cut. That's true. Also, you only added one edge, so you'd sort of think it would only go up by one. That's also true. Okay? So h of G is at most h of G hat, which is at most h of G plus 1. Remember, h need not be an integer. Right? It's a I mean, if it's exact, it's going to be an integer. But it's a semi-definite program, we don't know what it is. Okay? But so h will only go up, but it's only going to go up by at most 1 when you add an edge. Okay? So given that, corollary, even with a semi-random adversary, SDP is exact with high probability for exactly the same gap between P and Q. Also, don't forget that as a relaxation, it is always the case that h of G is at most the value of the actual min bisection. Okay, that's true always, right? Just by virtue of being a relaxation. So proof, all right, so it's just by induction. Okay, so we start with the random instance, right? So we start with the initial planted instance where this key lemma says the SDP is exact. Now we just go by induction on the changes the adversary makes to the graph, and we argue that every edge change it makes, an addition or a deletion, it remains exact. What can the adversary do? It can add an edge, or it can delete an edge. So if the adversary adds an edge, well, before it did this held with equality. That's the key lemma, right? H equals B. Okay? It adds an edge. It has to do it to the dense region. So B is the same. Okay? Initially, H and B are the same. It adds an edge. B doesn't change at all. This says H can only go up. Right, so think about it this way. Right, so over here we have H. Over here we have B. We're at a point where they're equal. If you add it to a dense region, B stays exactly the same. The homework problem says H can only go up. On the other hand, H has to always be at most B. Okay? So it can't go up. It has to stay exactly the same. So H still equals B. Case 2, the adversary could delete an edge. If it deletes an edge, it has to be from the bisection. So then the bisection, the minimum bisection, definitely drops by +1 for sure, because the adversary just removed it from the bisection. Right? So then case 2, H and B were equal. B drops by 1. The homework says H drops by at most 1. But again, H cannot drift above B. Right? So H has to drop by the maximum possible amount, exactly 1, and it can't drop by any more than that. H and B are still the same after the deletion. Okay? So, etc. Say proof by picture. Or do you want me to write it down?
No.
It's late in the day, so everyone get that? Any questions? Whoop. All right. So the final comment to motivate another homework exercise. So what algorithm did I actually give you? I gave you an algorithm that successfully computes the value of the minimum bisection. What do? Solve this SDP, or with high probability at least. Solve this SDP. If it says 127, then you say, cool, it's 127. Right. On the other hand, there's still the issue of actually extracting that bisection. And so you have to do a little bit of extra post-processing to do that. Okay? So post-processing, it's not hard, especially with the suitable hint. It's definitely not hard. Post-processing yields the planted bisection. Questions?